Okay, good morning, friends. We have seen yesterday theory of vibration. We have started with some of the basic principles of theory of vibration, and we have seen this content. Then we have seen what is the difference between static and dynamic problems. We have said as we add the factor of time, then we can convert our static problem to the dynamic problems. Then we have seen how to calculate total displacement by using static and dynamic problem. Then we have seen certain basic definitions. After this, we have tried to see several applications of this vibration theory in various field. So these are the various, you can say the applications. And then we have seen as the time is only not the factor which convert the static problem into the dynamic one, it should associate it with certain vibrations. So when the vibrations will be introduced into the systems, then your static problem will convert into the dynamic problems. We have seen these three examples. Then we have tried to define the vibrations with the case of single pendulum, and we have seen it is the process of continuous exchange of energy on application of time dependent force of the load, and based upon this we defined several components of vibration. Once this component has been defined, we have seen what is called as the degree of freedom, and based on this degree of freedom we have also seen various cases for how to calculate the degree of freedom for different systems, vibrating systems. And finally, we have seen the degree of freedom is not an intrinsic properties of the system, as it depends upon the boundary and other loading conditions. Then we tried to again came back to the component of vibration, and we have seen this potential energy we have actually converted to the spring. Kinetic energy we have associated with the mass, and the dissipation or the loss of energy we have connected with damping. So if I connect it all three, then I can say it is a mass spring damper type of relations, and that is VOC. Now if you go further, then you will arrive at this particular slide. You can see here I'm trying to draw a vibrating system with help of this particular phenomena, which is mass spring damper MSD system. So any vibrating system you can actually convert to this particular form. So if I see this is, if I convert this particular pendulum case where the mass m is there and which is rotating to the rotational angle theta, however this theta is being converted to your you can say the u, which is a displacement, right? This is connected with the damper, which is the component of loss of energy, and this is also connected with the spring. So this is mass spring dashpot. This is a notation of a dashpot type of system for the free vibrations. This particular system I'm supposed to take in the case of single degree of freedom system. So I'm writing here SDOF, which is single degree of freedom system. So right now I'm assuming this particular vibrating system in a single degree of freedom system. So this is a simple vibrating system with single degree of freedom system. Now see, first let us let us find out. You can see the free body diagram of this particular system. So already it is drawn here, but I will try to put it here. So the same mass I'm putting here. So this is my mass if I'm drawing the free body diagram, and this is the initial force is been given with respect to time t. So that force is pt. So this pt is acting on this particular direction. So I'm putting the pt here, right? So I need to take the pointer so that you will realize now this all mathematical terms. So I'm putting the pt here, which is in this direction. Then I have two forces. One is here, which is a damping force, which is acting here. So I'm putting this FD, which is my damping force. and then my spring force, which is also in this direction as my block is moving in this direction due to this force. So I'm taking, you can say, my spring force in this direction. Now against the motion, there will be the inertia force is also going to act. So this inertia force is also acting, which is in the direction opposite to the motion. So this is my inertia force. So this is 3 force which is going in this direction. And under this particular system will have a displacement which is also time dependent, which is u of t, right? Which is u of t. Now this mass will going to act in a downward direction with mg force, and similarly the reaction force which is on this particular roller, which I assume to be a frictionless, which is mg by 2, which is also nullified. Now if I want to develop the equation for vibrating system, then I need to use this particular principle which is called as the D'Alembert principle. So what it say, let us see. For any object in motion, the externally applied forces, internal forces, and the forces of resistance from a system of forces is in equilibrium. So for example, he is saying externally applied forces, you can see this. So externally applied forces, internal forces, and the forces of resistance from the system are in equilibrium. So basically I need to take this whole system into the equilibrium. Then I need to sum it up all the forces which is in the horizontal as well as in the vertical direction. If you see, vertical direction forces is nullifying. So I'm not taking this vertical direction forces, but the horizontal side. So if I'm taking this forces which is going on a horizontal side, so this is Fi, which is my first, plus damping force plus spring force, and this direction is different. So this is equals to Pt. So I'm arriving at this particular equation. I hope it is clear. So means this is as per the D'Alembert principle. Now let us see the characteristics of all these forces individually. So let us try to see all these forces individually. So let us see. So if I define the nature of inertia force, then if I draw a plot between Fi versus u, here I am taking acceleration here. So it is nothing but the double derivation of the displacement, which is this double derivative of this displacement, which is nothing but the acceleration. If my force is going to be in acceleration, if you give the force from here, so as you are giving the force from here, so basically this mass will actually move in this direction with certain acceleration. So basically the inertia force will acting in an opposite direction to the motion with the value F is equal to ma. So this A I have defined in terms of, you can say, this displacement, which is the double derivative of this displacement, and that's why I've drawn the graph. This is between inertia force versus acceleration. As per the Newton's second law, Fi is equal to m into A. So in this case, this is m into u double dot of t, or you can say u double dot. You can, both the same. You need to consider it is the time varying phenomenon. So this Fi, where this, if you draw a graph which is the linear graph, and this will give you the value of m. So basically this equation is valid only for this conditions where the mass is remain constant. If suppose you have certain condition where the mass is not going to remain constant, in which this particular condition will not valid. So this is, so we have defined the value of Fi here. Please remember that we will put in the previous equation later on. So this Fi is nothing but mu double dot of t. Now let us define the another quantity, which is this Fd. So this Fd is this. So sorry, Fs let us define. So Fs, if I'm assuming, then I am drawing the graph between Fs and u of t. As you know, the stiffness, if you know the relation of stiffness, which is K, is nothing but the force into the displacement. Force into displacement. I am taking the force which in terms of Fs, and the displacement I am supposed to assume which is u, right? So I am going to draw this particular curve which is Fs versus u of t. So if you plot this curve, then the slope of this curve will give you the value of stiffness K, right? So this relation will become Fs. This is for if I am putting the linear spring in the formula. For example, if you see in this case, you have put the linear spring, right? If I put the linear spring, then this value will comes around. This is Fs is equal to K into U. But in some time, this graph will not be a linear. It may be a curvilinear. For example, if you see this case, this is the particular type of phenomena in which the stress is increasing with a displacement, and with a very small displacement, the stress increase is quite higher. This is the kind of increase which we generally called as strain hardening. Generally, the strain hardening is happening in the case of rigid beam. In this case, this equation of K will not be a linear, and you cannot use this equation into the vibrating formula. In this case, you need to use the equation which is the you can say the linear curvilinear equation basically. So the curvilinear equation may have any form. You can say the alpha into gamma square or something like this that you need to use. However, for time being, we are not using this curvilinear equation. However, for your explanation, we are going to see this two curve. Another formula, another curve that you generally encountered, which is like this. You can see in comparison to this curve is having lot of displacement in comparison to this, and this is the general formula which is happening in the case of, this is the phenomena which is known as strain softening phenomena. Generally in a wide cables, aluminum cables, what you are seeing for the electricity or the power transmission lines, when you test it in the UTM, you will find out such type of graph for the stiffness measurement. So this is the form which called as strain softening phenomena. So this is also the graph, you can actually get it in the nature. However, for this vibrating purpose, we are actually seeing the linear spring. We are assuming the linear spring, and we will take this particular curve with the assumption that our spring is linearly connected to the vibrating system. Third point, which is the FD. The FD, which is the damping. Generally, the damping is being associated with the value of velocity of the vibrating system. So basically, when you are putting this vibrating system with the velocity, I need to draw the graph between FD versus velocity, which is nothing but the single derivation of displacement, which is u of t. Again, the condition is that I need to join this particular damper with the vibrating system in a linear direction. This equation is only valid in the case of linear vibrating system. So if you draw a curve between FD and UT, you will again find a straight line. So this is a straight line you will get, and the slope of this will give you the value of damping coefficient, right? So this is the damping coefficient that you will get, right? Okay. Now, if it is not remain linear, in this case, you may see the curvilinear phenomena. Generally, in the case of chimney or the very high-rise structure, which is subjected to wind load, generally what is happening, if there is a structure and the wind load is been coming, the wind load is the aperiodic, and it will actually vibrate you can say the structure as a system. In this case, your damping will be curvilinear, right? So, but however, again in the SDOF system, we are going to consider the linear spring for the modeling. So my value of FD will comes around C into U dot of T. So all three this equation, if I put it into the formula, which is Fi Fd plus Fs is equal to P of T, what we have seen earlier. If I put the value of M, which is nothing but M into D square U by dt square, plus FD, we have seen C into du by dt, plus Ku is equal to P of T. So if I can write this formula in terms of dot, that is Mu double dot plus Cu dot plus Ku is equal to P of T. And this equation is being known as governing equation of motion. So basically, if you see any vibrating system, first you need to transfer this particular equation into the basic governing equation of motion, right? So you need to see how it is to be converted. Now, based upon that, let us see what are the different classification system. So again, I'm taking the same MST system where the mass is on roller, and I'm assuming this roller is a frictionless. There is no friction is actually happening here. It is smoothly moving. It is connected with the spring, which is having a stiffness K, and the damper with the damping coefficient C. And if I give the force P of T here, under the action of P of T, the displacement of this particular vibrating system is U of T. Now, based upon this MST system, let us define various type of vibrations. So basically, if I want to classify the vibration, as you know, the vibration will be of generally two types. The first is the free vibration and other is forced vibration. If you see free vibration, when the free vibration happens, when after the initial disturbance to this particular mass, if I'm not giving repeated value of P of T, means external force P of T is 0, in this case, this particular system will vibrate with a natural frequency, and this particular vibrating system is known as free vibration. Similarly, just a reverse of this, if I want to define a forced vibration in which I need to give the force P of T or external force P of T to continue the vibration of this particular vibrating system. So at a repeated interval of time or at some interval of time, I need to keep on giving the value of P of T or the external force. Then the particular vibrating system is called as P of T. It means the P of T is not 0, it is having some value. So this is P of T is not 0 in this equation. Then the particular vibrating system is known as forced vibrating system. Again, based on the damping characteristics, again I will classify this particular vibration into the another two category, that is undamped vibration and the damped vibration. Both in the case of free and forced vibration, these two category will happen. So this is damped vibration and this is undamped vibration. So if I see, if you are putting the value of damping, so this damping value is not equals to 0, then what will happen is this particular vibrating system will stop after some period of time. So basically, if I take C is not equals to 0, then I may have some value of damping and P of T is equal to 0, then particular system is known as damped free vibration. Similarly, if I'm not considering the value of C, I'm assuming that the damping is 0, there is no loss of energy, then C is equal to 0 I can take. And if I have the combination of this like a P of T is equal to 0, then I can say the particular system is vibrating in undamped free vibration mode. Same as in the case of forced vibration, if you have P of T, external force is absent, and if you have a damping force equal to 0, then this force is known as undamped free vibration. And if suppose the damping force is not equals to 0, in this case you can consider it is damped force vibration case. Now let us go further. If I define this force vibration into the another two category, which is periodic and aperiodic case, then the periodic means when the particular vibrating system will vibrate with equal interval of time. For example, if I draw a response versus P of t and t, if I give this external force P of t to the system with equal number of time, you can see this is a P of t, but I am repeating this particular force with certain equal duration of a time, duration or the period, then this particular system is known as periodic. You can see the time interval is almost the same. However, I have drawn hand figure, so you can see this P of t is given with the equal time. This is equal time. Okay, this is all equal times. So this is a periodic motion. But if it is not exist, for example, this P of t is not equals to 0, if it is happening in this way, then the condition will be remain like this. In this case, you can see the P of t is not repeating with the regular interval of time, and then this particular system is known as aperiodic one. In the aperiodic one, in aperiodic, undamped force vibration can happen, or aperiodic damped force vibration can happen. In the aperiodic vibration, again, I will divide into the two part. One is called as the transient aperiodic undamped force vibration, or whatsoever you take. So I will define in a transient and the steady state. Now, what is a transient? If my time period is limited, means my vibration will stop after limited period of time, after finite period of time, like this. You can see this vibration is having, you can say the time period, it is continuing up to this much time. At finite interval of time, this vibration is being stopped. Then this particular vibration, which is aperiodic in nature, is called as transient aperiodic motions. But in a reverse way, if this time period is continue for infinite period of time, you can see this is extending to the infinite period, then in this case it is called as steady state vibration. So I can give an example of transient, which is earthquake load, which is for steady state, a steady period of time, or you can say the limited period of time, finite interval of time, while you can say the wind load, which is existing on the structure, which is for the infinite period of time. However, both the case is of aperiodic in nature, right? Because the duration of giving the external force is not constant. So this way you can take the various forms of vibration. So I hope you have clearly understood what are the different modes of vibrations: free, force, undamped, damped, periodic, aperiodic, transient, and the steady state one. Now further we will see each and every vibrations in detail. Let us first understood, we have already taken the example of horizontal vibration case, and we have defined the governing equation of motion, which is this, which is mu double dot plus cu double dot plus ku. Here the displacement, you can please do not confuse with this x, because in this, suppose you consider the displacement value is x of t, in this case this value will come. Okay, this x or u is same, whatever the value of displacement that you are assuming. Okay, same equation. So basically the forms of equation for the horizontal case that you have assumed is this. You have considered this is a horizontal, in a horizontal direction this particular system is vibrating, right? Now if I consider this in the vertical way, for example, if I take the spring in this way, so this is the spring I have attached to the fixed support. Now on this particular spring I am putting the value of mass m. So this is my reference point I am considering once I am putting the m. So as long as I am attaching the m, this particular spring will actually stretched under the force of static force. So this is my static displacement delta st from the reference point. So I'm taking delta static value, and then what I'm doing is I'm giving to this particular system the external force P of t, or initial disturbance. In this case, what will happen is I'm not giving P of t, I'm giving the initial disturbance to this particular force, so that this particular system will having the dynamic vibration or dynamic displacement of z of T. So at this point, this particular vibrating system will vibrate in this way, right? So I'm taking one directional displacement, which is Z of T. Now let us understand the free body diagram of this. So the same mass I have plotted here. So mass I have plotted. So it is attached with the spring. So the spring will act in a direction opposite to the motion. As the mass is moving in this direction, my spring force will be in this direction. You have given the P of T, which is in this. So I am considering P of T here. Load, or you can say the mass mg, will act in a downward direction, that is a weight, and the inertia force, which will also act opposite to the motion. So this is the free body diagram. If I am considering the D'Alembert principle, then I need to consider this particular system is in the equilibrium. So this is Fi plus Fs, both these forces, which is equals to mg plus P of T. If I take the value of Fi, which is nothing but mass into double derivation of displacement. So this vibrating system is having the displacement, that is Z of T. So I can take m into Z double dot plus now the spring system. So I need to consider the value of Fs. So total displacement of the spring will be delta static plus Z of T. So this is my displacement, and Fs value I can take k into the displacement of the spring. So that is delta static plus Z of T or Z, whatever the value you take, which is equals to mg plus P of T. Now, if you multiply this k into this, so this will come mz double dot plus k into delta static plus kz is equal to mg plus P of T. Now, if you understand the spring like this, if you understand the static system, so this value will be mg, which will act in the downward direction, which will act in the downward direction like this. Okay, so which will act in a downward direction to this. Now just see what is going to happen. So if suppose I will take in this way, suppose this is a spring. So this is your mass mg, which is in the this direction. So this particular spring will be stretched. If I take the value of k, which is nothing but w upon displacement of the spring, which is in this case is delta static. So w is equal to mg I am supposed to take. So the mg is equal to k into delta static. So here you can see k into delta static I can replace with help of mg. So if I replace this with mg, then this mg is going to be cancelled here, and then equation will comes mz double dot plus kz is equal to P of T. If you see, if the damping is not exist, then it is the same equation what we have developed for the horizontal vibration. So you can say that the governing equation of the vibration, which remains same in both horizontal as well as in the vertical system, right? So this is so means you can say that the vibration equation remains same irrespective of the direction of the vibration. So I will stop it here. If you have any questions, you may actually put in the chat box. I am able to actually answer it. Thank you very much.